need to enforce access control on resources and prompts without cluttering your core logic with permission checks. You'll see how to create middleware that inspects component metadata, like tags and enabled status, before allowing operations to proceed, using FastMCP's built-in hooks for resource reads and prompt retrieval. The pattern keeps security logic centralized while letting your main code focus on functionality.
From FastMCP server middleware, import middleware. Middleware context. From FastMCP exceptions, import resource error, prompt error. Class component access middleware, middleware. Async def on read resource, self context. Middleware context, call next. If context, FastMCP context. Try. Resource equals await context, FastMCP context. FastMCP get resource context, message URI. If restricted in resource tags. Raise resource error, access denied, restricted resource. Accept exception. Pass. Return await call next, context. Async def on get prompt, self context. Middleware context, call next. If context, FastMCP context. Try. Prompt equals await context, FastMCP context. FastMCP get prompt context, message name. If not prompt enabled. Raise prompt error, prompt is currently disabled. Accept exception. Pass. Return await call next, context.
This demonstrates the interceptor pattern applied to resource and prompt access control in FastMCP's middleware system. The pattern creates transparent validation layers that inspect and potentially block operations before they reach core handlers, without requiring modifications to the underlying components. What makes this distinctive is its non-invasive nature. Security rules are enforced externally, keeping business logic clean and uncluttered by access checks. The interceptor works by wrapping the execution pipeline with pre-processing hooks that examine both the request context and the target component's metadata. When a request arrives, the middleware fetches the component's full definition, including custom tags like restricted, performs validation against business rules, and either raises domain-specific exceptions or proceeds with the original operation. This creates a separation where access policies live in dedicated middleware layers, while components remain focused on their core functionality. This approach solves the common problem of scattered authorization logic across codebases. By centralizing access rules in middleware, you gain consistent enforcement across all entry points, simplify component testing, no need to mock auth contexts, and make policy changes without touching business logic. The trade-off is slightly increased latency from the additional validation layer, but the maintainability benefits typically outweigh this cost in security-sensitive applications. Let's break it down line by line.
From FastMCP server middleware, import middleware. Middleware context.
This imports the base, middleware, class, and its middleware context type, the foundation for FastMCP's request interception system. Middleware lets you inspect, modify, or block requests before they reach the core handlers, enabling cross-cutting concerns like access control and validation. The context object carries request metadata and shared services between middleware layers.
From FastMCP exceptions, import resource error, prompt error.
Imports custom exception classes for access control. Resource error handles restricted resource attempts, while prompt error manages disabled prompt scenarios, both critical for the middleware's security checks.
Class component access middleware, middleware.
This defines a middleware class that intercepts and validates FastMCP operations. It implements the middleware interface, allowing it to hook into the request pipeline before core handlers execute. The pattern enables cross-cutting concerns like access control without modifying individual components.
Async def on read resource, self context. Middleware context, call next.
This is the middleware hook for resource read operations. It intercepts every read resource call, allowing preprocessing like access control before delegating to the next middleware via call next. The pattern enables clean separation of concerns in the request pipeline.
If context, FastMCP context.
This is a defensive check for FastMCP context availability. It prevents null reference errors by only executing resource access logic when the context exists, which is critical in middleware where context may not always be populated. The pattern ensures graceful handling of missing context without crashing the pipeline.
Try.
The try block implements defensive programming, isolating error-prone operations to prevent crashes. It ensures that if resource access or prompt validation fails, the middleware gracefully continues execution rather than propagating exceptions. This pattern maintains system stability when dealing with external dependencies like FastMCP's resource and prompt APIs.
Resource equals await context. FastMCP context. FastMCP get resource context. Message URI.
This fetches the resource object from FastMCP using the URI from the incoming message. It's the access check step. Before allowing the read operation, we verify the resource exists and inspect its tags for restrictions. The await indicates this is an async call to the FastMCP server's resource store.
If restricted in resource tags.
This checks for a restricted tag in the resource metadata, implementing access control. It enforces security by blocking read operations on tagged resources before they reach downstream handlers. The pattern is common in middleware, early validation to fail fast.
Raise resource error, access denied, restricted resource.
This raises a resource error when encountering restricted resources, enforcing access control. It's the security gate that prevents unauthorized access to tagged resources, failing fast with a clear error message. The pattern ensures restricted content never reaches the middleware chain.
Accept exception.
This is a defensive exception handler. It silently catches any unexpected errors during resource or prompt validation, ensuring the middleware chain continues even if validation fails. This prevents validation issues from breaking the entire request flow.
Pass.
This is a silent exception handler. When resource or prompt checks fail, it absorbs the error and continues execution, preventing middleware from breaking the request chain. This pattern maintains graceful degradation when FastMCP context operations encounter issues.
Return await call next, context.
This is the middleware chain continuation pattern. It delegates to the next middleware in the sequence, ensuring all middleware layers execute in order. Without this, the pipeline would terminate prematurely, breaking the chain of responsibility.
Async def on get prompt, self context. Middleware context, call next.
This is the middleware hook for prompt retrieval, part of FastMCP's middleware pipeline pattern. It intercepts get prompt operations to enforce business rules before the request proceeds, like checking if a prompt is enabled. The call next parameter maintains the chain of responsibility, allowing subsequent middleware to process the request.
If context, FastMCP context.
This is a defensive check for FastMCP context availability. It prevents null reference errors by only executing context-dependent logic when FastMCP context exists, which happens when the middleware is properly initialized within a FastMCP server instance. This pattern ensures graceful handling of both initialized and uninitialized states.
Try.
The try block implements defensive programming, isolating error-prone operations to prevent cascading failures. It ensures that even if resource or prompt validation fails, the middleware continues processing by silently swallowing exceptions. This pattern maintains system stability while enforcing access control rules.
Prompt equals await context, FastMCP context, FastMCP get prompt context, message name.
This fetches the prompt configuration by name from FastMCP's prompt registry. The middleware uses this to check if the prompt is enabled before allowing access, enforcing runtime prompt governance.
If not prompt enabled.
This checks if the prompt is disabled before allowing access. It enforces prompt availability rules, preventing AI calls to inactive prompts that shouldn't be executable. The pattern mirrors the resource restriction check earlier, creating consistent access control across different asset types.
Raise prompt error. Prompt is currently disabled.
This raises a prompt error when a disabled prompt is accessed, enforcing prompt availability rules. It prevents AI models from using deactivated prompts, maintaining system integrity. The pattern mirrors the resource restriction check in on-read resource, creating consistent access control.
Accept exception.
This is a defensive exception handler that silently swallows all errors during resource and prompt validation. It ensures failed validation checks don't crash the middleware pipeline, allowing the request to proceed through call next, even when validation encounters issues. This pattern prioritizes system resilience over strict validation enforcement in this middleware layer.
Pass.
This is a silent exception handler. It deliberately swallows any errors during resource or prompt validation, allowing the middleware chain to continue processing the request. This pattern prevents validation failures from crashing the entire request pipeline.
Return await call next, context.
This is the middleware chain continuation pattern. It explicitly passes control to the next middleware in the stack, ensuring the request processing pipeline completes even if this middleware doesn't modify the context. Without this, the chain would terminate prematurely. FastMCP access control pattern. This middleware demonstrates how FastMCP2 enforces access rules by intercepting resource reads and prompt requests, using tags and enabled flags as policy anchors. Silently swallowing exceptions in the try-except blocks means failed lookups will proceed as if no restriction exists, which may expose unintended resources. The same metadata that powers access control also enables dynamic behavior modification without code changes.
The middleware that knows nothing of your rules becomes the strictest enforcer of them all.